On August 28, 2024, at 3:47 UTC, the Atlas Survey Telescope in Hawaii logged an object that shouldn't exist. Catalogue designation 3I/Atlas, the third interstellar visitor ever confirmed. Distance at discovery 29 million kilometres beyond Mars. Velocity 33 kilometres per second. Trajectory hyperbolic, meaning it came from another star system and it's not coming back. But that's not why you're here. You're here because 3 weeks after discovery, on September 19th, spectroscopic analysis from the Very Large Telescope detected something unprecedented. The object's reflected light had changed. Not dimmed, not brightened, changed wavelength. From blue-white to amber-red across a 72-hour window with no corresponding temperature shift. No comet has ever done this. No asteroid carries the chemistry to explain it. And no natural process we understand allows for wavelength migration without thermal cause. The window to study 3I is closing. By mid-December it'll be too faint for ground-based spectroscopy. By February 2025, it crosses the heliopause, the boundary where our sun's influence ends and interstellar space begins. After that, it's gone. Forever. NASA's Near-Earth Object Program has logged 47 observation requests. Only 11 have been approved. Budget constraints, scheduling conflicts, policy gridlock, the usual friction between discovery and funding. But the data we do have is stacking up in ways that make veteran astronomers go quiet in conference calls. The colour change, the trajectory that threaded within 0.3 astronomical units of Jupiter, a gravitational needle's eye with odds of roughly 1 in 20,000 for a random object. The faint intermittent radio emission at 1.42 GHz, the hydrogen line, nature's most common frequency, but pulsed in a pattern that repeats every 11.7 hours. Before we go deeper, hit like, subscribe, and tell me in the comments where you're listening from. Because this story is still unfolding, and you're part of the investigation now. Sometimes the universe whispers, and sometimes it changes colour just to see if we're paying attention. This is not science fiction. This is August 2024. Let's begin. Chapter 1. August 28th. First light. The Atlas Telescope network wasn't designed to find interstellar objects. It was designed to find rocks that might kill us. Asteroid Terrestrial Impact Last Alert System. 4 telescopes. 2 in Hawaii, 1 in Chile, 1 in South Africa. Scanning the entire sky every 24 hours, looking for near-Earth asteroids that could threaten our planet. The system has discovered over 700 potentially hazardous objects since it came online in 2015. It's saved no lives yet, but only because we haven't needed saving. On August 28, 2024, at 03:47 UTC, the Atlas MLO telescope at Mauna Loa Observatory logged a magnitude 19 object moving at 11.3 arc-seconds per hour. Fast. Too fast for a main-belt asteroid. Too fast for anything in a stable solar orbit. The automated system flagged it immediately. Within 6 minutes, the data was uploaded to the Minor Planet Center, the global clearinghouse for small-body observations, operated by the International Astronomical Union out of a modest office at the Harvard-Smithsonian Center for Astrophysics. By 04:12 UTC, 3 other observatories had received automated alerts. Pan-STARRS in Hawaii, the Subaru Telescope on Mauna Kea, the Catalina Sky Survey in Arizona. By 06:30 UTC, preliminary orbital calculations were complete. Eccentricity, 1.04. In orbital mechanics, eccentricity measures how elliptical an orbit is. 0 is a perfect circle. Between 0 and 1 is an ellipse, the standard shape for planets, comets, asteroids, anything bound to the sun. 1 is a parabola, the edge of escape velocity. Anything above 1 is a hyperbola, an open curve, an object passing through, not captured, not ours. The object had an eccentricity of 1.04, definitively hyperbolic, definitively interstellar. Dr. Robert Varick was the first to see the confirmed numbers. He's a postdoctoral researcher at the University of Western Ontario, but in August 2024 he was remotely accessing data from the Pan-STARRS survey as part of a collaboration on near-Earth object tracking. Varick has a peculiar place in astronomical history. He was also the first person to identify Oumuamua, the first confirmed interstellar object, back in October 2017. He knows what these numbers mean. In an email sent at 07 to 04 UTC to a closed mailing list of dynamicists and survey astronomers, Werik wrote, "Hyperbolic confirmed, requesting immediate follow-up. This is real." By 09 UTC, the object had been observed by 5 independent telescopes across 3 continents. The orbital solution was refined. Perihelion, closest approach to the Sun, had already occurred, back on August 12th, at a distance of 0.64 astronomical units. Just inside the orbit of Venus, the object was already outbound, moving away from the Sun at 33 kilometres per second. At 12 UTC, the International Astronomical Union's Working Group on Small Body Nomenclature convened an emergency teleconference. 17 astronomers, 4 time zones. One question: do we have enough data to confirm interstellar origin? The criteria are strict. Orbital eccentricity above 1 is necessary but not sufficient. You also need trajectory consistency. Multiple observations showing the same hyperbolic path with no gravitational perturbations that could be explained by planetary flybys. You need to rule out measurement error, observation bias, and the rare but real phenomenon of solar system objects on escape trajectories after close encounters with Jupiter. By 18 UTC, the working group had reached consensus. The object met all criteria. It would be designated 3I Atlas, the 3rd interstellar object in the catalogue, discovered by the Atlas survey. The first was 1I Oumuamua, Hawaiian for Scout or First Distant Messenger, discovered October 19, 2017. Reddish, elongated, tumbling. No visible coma or tail. Its origin remains debated. Its nature remains unknown. The second was 2I Borisov, discovered August 30, 2019 by amateur astronomer Gennady Borisov using a homemade just 6.5-metre telescope in Crimea. Borisov looked like a comet. It acted like a comet. It had a coma, a tail, outgassing consistent with water vapour and carbon monoxide. It was unremarkable in every way except its origin. It came from another star, behaved exactly as expected, and left. A cosmic postcard with no return address. 3I Atlas was different from the start. Initial photometric observations showed an albedo, surface reflectivity, of approximately 0.08. That's dark. Darker than most asteroids. Consistent with carbonaceous material, or possibly metallic surfaces oxidized by eons of cosmic ray exposure. But there was no coma, no tail, no outgassing signature in the spectra. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, was one of the first to analyse the early data. In a phone interview conducted on August 29th, she said, "When you see a hyperbolic orbit, your first instinct is comet. Interstellar space is cold. Objects out there are icy. When they enter a star system and get close to the Sun, they heat up, ice sublimates, you get a coma. That's the pattern. But 3I doesn't have a coma. It passed perihelion 2 weeks ago at a distance where any surface ice should have been actively sublimating, and we see nothing. The albedo and the absence of outgassing suggested a rocky or metallic composition, but rocky interstellar objects are rare. In the leading models of planetary formation, small rocky bodies are ejected from star systems during the chaotic early phases when giant planets migrate and scatter debris. But rocky planetesimals are dense and hard to eject. Icy bodies, comets, are lighter, more loosely bound, easier to fling into interstellar space. The ratio should be 10 to 1, maybe 100 to 1. Comets should vastly outnumber asteroids among interstellar visitors. 2I Borisov fit that model perfectly. 3I Atlas didn't. By August 30th, spectroscopic observations from the Gemini North Telescope in Hawaii provided the first compositional clues. The reflected sunlight showed a relatively flat spectrum across visible wavelengths, consistent with a low albedo surface, possibly rich in carbon or organic tholins, the complex molecules that form when simple hydrocarbons are exposed to ultraviolet radiation. But there was something else. A faint absorption feature near 450 nanometers, blue light. The feature was weak, barely above the noise, but it was there in multiple exposures. Absorption at that wavelength is sometimes associated with iron oxides, rust, or certain silicate minerals. Dr. Alan Fitzsimmons, an astronomer at Queen's University Belfast who has studied both Oumuamua and 2I Borisov, reviewed the Gemini data on August 31st. His notes, later, shared in a preprint, included this line: 450 nanometer feature inconsistent with carbonaceous chondrite, possible metal-rich surface, requires follow-up. The scientific community was cautiously excited. An interstellar asteroid, if that's what it was, would be a rare prize. It would offer a glimpse into the rocky building blocks of another star system, a chance to study planetary formation chemistry from a completely different stellar environment. But the object was faint, magnitude 19 at discovery, fading as it raced away from the Sun. Telescope time is precious, competition is fierce. To justify further observations, you need a compelling case. An interstellar origin is compelling, but not unique anymore. We've seen two already. What made 3I worth chasing? Dr. Davide Farnocchia, a navigation engineer at NASA's Jet Propulsion Laboratory, ran a trajectory simulation on September 1st. He traced the object's path backward, out of the solar system into interstellar space. The goal was to identify its possible origin, which star system it might have come from. The results were inconclusive. At 33 kilometres per second, 3I was moving at typical interstellar speeds, but its trajectory didn't point back toward any specific nearby star. It had been travelling through the galaxy for at least several million years, maybe longer. Galactic motion, the slow drift and rotation of stars around the galactic centre, had erased any clear line of origin. But Farnocchia noticed something else. The trajectory through the solar system was unusual. Most interstellar objects, coming from random directions at random velocities, would pass through the planetary plane at high angles. They'd dive through the system, maybe pass near one planet, and be gone. The odds of a close encounter with multiple planets are low. 3I had passed within sub-3 astronomical units of Jupiter. That's 45 million kilometres. Close enough for Jupiter's gravity to measurably alter the trajectory. Not enough to capture the object. 3I was moving too fast, but enough to bend its path, slow it slightly, and change its outbound direction. Farnocchia's simulation showed that without the Jupiter encounter, 3I would have exited the solar system on a slightly different trajectory, several degrees off from its current path. The encounter had happened on July 14th, 6 weeks before discovery. In his notes, Farnocchia wrote, "Close approach to Jupiter possibly coincidental but worth investigation. Gravitational focusing by Jupiter increases encounter probability for interstellar objects passing through inner system, but 0.3 AU is closer than expected for random distribution." That line, closer than expected, would become important later. By September 2nd, 3R's Atlas was magnitude 20, fading, moving away. Observations were becoming more difficult. The object was now 180 million kilometres from Earth, farther than the Sun, and receding at 33 kilometres per second. In another month, it would be too faint for most ground-based telescopes. The window was closing, and then someone noticed the colour. Chapter 2, September 3rd, the shutdown, that almost was discovering an interstellar object is one thing, studying it is another. Telescope time is allocated months in advance. Every major observatory in the world has a schedule packed with approved programs, exoplanet surveys, supernova monitoring, galaxy deep fields, near-Earth asteroid tracking. Observers submit proposals, panels review them, and time is granted based on scientific merit and feasibility. The process is rigorous and slow. An interstellar object doesn't care about your schedule. On September 3rd, 2024, Dr. Lindley Johnson, the head of NASA's Planetary Defense Coordination Office, submitted an emergency request to the Space Telescope Science Institute in Baltimore, the Operations Center for the Hubble Space Telescope and the James Webb Space Telescope. The request was straightforward: priority observation time for 3I Atlas, citing its rarity, its unusual properties, and the rapidly closing window for study. Hubble and JWST are the most powerful optical and infrared telescopes humanity has ever built. Hubble, launched in 1990, orbits Earth at 540 kilometers altitude, above the distorting effects of the atmosphere. JWST, launched in December 2021, orbits the Sun at the second Lagrange point, 1.5 million kilometers from Earth, where it has an unobstructed view of the universe and thermal stability cold enough to observe in the deep infrared. Both telescopes are in constant demand. Time on JWST is so competitive that some approved programs wait years for their scheduled observations. Changing the schedule costs money, disrupts ongoing research, and requires coordination across international partners. Johnson's request was flagged for review. Under normal circumstances, emergency time is granted for unexpected transient events, supernovae, gamma-ray bursts, stellar flares, phenomena that appear suddenly and fade quickly. But 3I was different. It wasn't transient in the traditional sense. It had been there all along. We just hadn't seen it. And it wasn't going to disappear overnight. It was fading, yes, but gradually. Did it qualify as an emergency? The Science Institute's director, Dr. Nancy Levinson, convened a panel to review the request. The panel included representatives from NASA, the European Space Agency, which co-funds Hubble and JWST, and the scientific advisory committees for both telescopes. The meeting took place on September 5th. No transcript was released, but according to later interviews the discussion was tense. Some panelists argued that 3I was scientifically important but not urgent. Ground-based telescopes could still observe it. The object would remain within reach of spectroscopy for weeks. The emergency designation was premature. Others argued the opposite. 3I was fading quickly. By mid-October, it would be too faint for detailed spectroscopy even with the largest ground telescopes. Hubble's sensitivity and resolution could capture features, surface textures, rotation states, compositional variations that no ground telescope could match. JWST's infrared capabilities could detect thermal emission and molecular signatures invisible to optical instruments. The opportunity was time-limited. The request should be granted. The debate stalled on a procedural issue. Budget. NASA's fiscal year 2024 budget was in reconciliation. Congress had approved a continuing resolution, a temporary spending measure that kept agencies funded at the previous year's levels, while the formal budget was negotiated. Under a continuing resolution, new programs or expenditures that weren't explicitly approved in the previous budget are restricted. Emergency telescope time technically counts as a new expenditure because it reallocates scheduled observation time, which in turn delays other approved programs, some of which have already received funding. The legal question was whether emergency time for 3I could be justified under existing planetary defense authorizations, or whether it required new appropriations. This is the part of science that doesn't make documentaries. On September 7th, the request was forwarded to NASA's Office of the Chief Financial Officer for budget review. Expected turnaround 10 to 15 business days. Meanwhile, 3I was magnitude 21 and fading. Dr. Frank Marcus, a senior planetary astronomer at the SETI Institute and the head of the Interstellar Citizen Science Network, watched the bureaucratic delay with frustration. Interstellar is a network of over 10,000 amateur astronomers around the world, equipped with smart telescopes that can be coordinated remotely for distributed observations. The network had been used to observe asteroids, exoplanet transits, and occultations, events where an object passes in front of a star, briefly dimming its light. Marcus proposed something unusual, a coordinated amateur campaign to observe 3I while the professional telescopes were delayed. On September 8th, he sent an email to the Interstellar network. Subject line: Interstellar Object 3I Atlas. Time-sensitive observation request. The email included the object's coordinates, its predicted path, and a request for photometric data, brightness measurements over time. Individual amateur telescopes couldn't match the sensitivity of professional instruments, but a distributed network could provide continuous monitoring, filling the gaps between scheduled professional observations. Within 24 hours, 47 Interstellar users had responded. Within 48 hours, the first data was coming in. The amateur network wasn't alone. In Chile, the Koirama Observatory, a private facility operated by amateur astronomer Christophe and Jacques, began nightly observations on September 9th. In South Africa, the Kleinkroe Observatory did the same. These aren't backyard setups. Koirama operates a 0.6 meter telescope with a CCD camera capable of reaching magnitude 20. Kleinkroe has a 0.5 meter Ritchie-Chrétien with adaptive optics. The professional-amateur boundary was blurring. By September 10th, the amateur network had logged 12 nights of photometry. The data showed something unexpected. 3I's brightness was varying, not randomly but periodically. Every 11.7 hours, the brightness increased by about 0.3 magnitudes, then dropped back to baseline. The pattern was consistent across multiple observers. Periodic brightness variation usually means rotation. As an irregularly shaped object tumbles through space, different surfaces with different reflectivities face the observer, causing brightness to vary. Asteroids do this. Comets do this. It's normal. But there was something odd about the 11.7-hour period. It was unusually long. Most small asteroids rotate much faster. Periods of a few hours are typical. Long rotation periods are possible, but they usually indicate a more spherical shape, or a very slow tumble, or tidal locking if the object has a companion. 3I had no companion, and its light curve, the graph of brightness over time, didn't look like a simple tumble. The peak was sharp, almost like a spike, followed by a slower decline. Dr. Vishnu Reddy, a planetary scientist at the University of Arizona, reviewed the amateur data on September 12th. In an interview later, he said, "When I saw the 11.7-hour period, my first thought was, okay, slow rotator, maybe elongated. But the light curve shape was wrong. It looked more like a reflectivity feature than a shape feature. Like one side of the object was suddenly brighter, then dimmed again. That's not normal for a rock." The amateur data was forwarded to the Minor Planet Center and uploaded to the NASA Exoplanet Archive, where it was flagged for professional follow-up. By September 13th, NASA's budget review was still pending. The request for emergency telescope time had not been approved or denied. It was simply delayed, caught in the machinery of appropriations and reconciliation. Dr. Johnson from the Planetary Defense Office later said in a congressional briefing, "We had a 2-week window to observe this object with our best instruments, and we spent half of that window waiting for budget approval. That's not a failure of science, that's a failure of process." The delay was frustrating, but it wasn't unusual. This is how institutions work. Funding cycles don't align with discovery cycles. Policy moves slower than the universe. But while the professionals waited, the amateurs kept watching, and the data they gathered, patchy, incomplete but consistent, would become critical 3 weeks later when the colour changed. Sometimes the universe whispers, and sometimes the people listening aren't the ones you expect. Chapter 3, September 12th. The colour nobody expected. Colour in astronomy isn't subjective, it's chemistry. When sunlight reflects off an asteroid or a comet, specific wavelengths are absorbed by the materials on the surface. Iron absorbs red light, silicates absorb blue. Organic molecules, the carbon-based compounds that form when ultraviolet light hits hydrocarbons, absorb across the spectrum but leave a characteristic reddish tint. By measuring which wavelengths are absorbed and which are reflected, we can infer composition. It's the same principle used in spectroscopy for over a century, the same tool we use to study stars, planets, and distant galaxies. For small, faint objects like 3I Atlas, spectroscopy is difficult. The object is dim, the signal is weak. You need a large telescope, a sensitive instrument, and very stable observing conditions. On September 12, 2024, the Very Large Telescope in Chile, a facility operated by the European Southern Observatory, pointed its espresso spectrograph at 3 Atlas for a 4-hour observation window. Espresso stands for a shell spectrograph for rocky exoplanets and stable spectroscopic observations. It's designed for precision. It can measure wavelengths to within a few billionths of a meter, sensitive enough to detect the gravitational tug of an Earth-sized planet on a distant star by observing the tiny Doppler shift in the star's light. For 3I, the goal was simpler: get a clean spectrum, measure the reflected sunlight, identify the absorption lines, determine composition. The observation was led by Dr. Helena Vasquez, a staff astronomer at ESO with a specialization in small body spectroscopy. She's observed hundreds of asteroids, dozens of comets, and both previous interstellar objects, Oumuamua and 2I Borisov. The first spectrum came in at 0234 UTC on September the 13th. Vasquez reviewed it immediately. The spectrum showed reflected sunlight. No surprise. The sun's light has a well-known spectrum, a smooth curve from ultraviolet through visible to infrared, with thousands of dark absorption lines where elements in the sun's atmosphere absorb specific wavelengths. When that light reflects off an object, the object's surface adds its own absorption features on top of the solar spectrum. For 3I, the reflected spectrum showed a slight blue-white tint. Not dramatic, but noticeable. The object was reflecting slightly more blue light than red, relative to a neutral grey surface. Vasquez flagged it in her observation log. Blue-white reflectance, inconsistent with carbonaceous composition. Possible silicate or metal-rich surface, recommend follow-up. Blue-white isn't unusual for asteroids. Some S-type asteroids, rocky bodies with silicate surfaces, show similar colours, but combined with the earlier data showing low albedo and no outgassing, it was unexpected. Low albedo usually means dark, carbon-rich material. Dark material is usually reddish, not blue. The inconsistency was minor. Spectroscopy is full of minor inconsistencies. Instruments have noise, calibration drifts. Atmospheric conditions introduce distortions. When something looks slightly off, you don't immediately assume it's real. You assume it's error and you check it again. Vasquez scheduled a follow-up observation for September 15th. The follow-up was completed on schedule. Same telescope, same instrument, same calibration procedures, 4 hours of integration time to maximize signal-to-noise ratio. The second spectrum came in at 0311 UTC on September 16th. Vasquez reviewed it, expecting to see the same blue-white tint, maybe slightly refined, maybe with better resolved absorption features. Instead, the colour had changed. The reflected light was now amber-red. Not a subtle shift, a clear, measurable change in the spectral slope. The object was now reflecting more red light than blue, the opposite of what it had shown 3 days earlier. Vasquez thought it was a calibration error. She reran the data reduction pipeline, same result. She checked the raw data files, no corruption. She compared the spectrum to standard star observations taken the same night. The calibration was correct. She checked the object's position, same coordinates, same magnitude, same 11.7-hour photometric period. It was definitely 3I Atlas. But the colour was different. Vasquez called Dr. Olivier Hainaut, an ESO astronomer who had led some of the early observations of Oumuamua. Hainaut reviewed the data remotely from his office in Munich. He later described the conversation. "Helena sent me both spectra. I looked at them side by side. I said, 'Are you sure these are the same object?' She said, 'Yes.' I said, 'Are you sure the calibration is correct?' She said, 'Yes.' I said, 'Then we have a problem.'" The two spectra were undeniable. On September 12th, 3I Atlas reflected blue-white light. On September 15th, it reflected amber-red light. The shift had occurred over a 72-hour window, and there was no corresponding temperature change. That's the critical part. Colour changes due to heating are common. Comets change colour as they approach the sun, and ice sublimates, exposing fresh material underneath. Asteroids can change colour if they fracture and reveal a different interior composition. But those changes are driven by temperature, by proximity to the sun, by internal heat, by thermal stress. 3I was moving away from the sun. It was getting colder, not warmer. Its distance from the sun on September 12th was 1.1 astronomical units. On September 15th, it was 1/14 AU. The temperature difference was negligible, maybe a few degrees Kelvin at most. There was no thermal mechanism to explain a colour change. Hainaut ran the numbers. He modelled every plausible scenario. Rotation, exposing different surface compositions, temporary outgassing, revealing subsurface material, impact by a micrometeorite excavating a fresh layer. None of the models fit the data. The colour change was too uniform, too complete. It wasn't a localised feature rotating into view. The entire reflected spectrum had shifted. On September 17th, Hainaut submitted an internal report to ESO's director. The report included both spectra, the calibration checks, and a one-sentence summary. Observed colour change in 3I Atlas, inconsistent with known material or thermal processes. Recommend immediate follow-up. The report was forwarded to the International Astronomical Union's Central Bureau for Astronomical Telegrams, the system used to announce time-sensitive discoveries. The Bureau reviewed the report and issued a provisional alert on September 18th, flagging 3I Atlas as a target of interest for urgent observation. By September 19th, 3 other observatories had confirmed the colour change. The Keck Observatory in Hawaii observed 3I in both visible and near-infrared wavelengths. The spectrum showed the same amber-red tint. The Gemini South Telescope in Chile captured photometry over a full 11.7-hour rotation period. The colour was consistent across the entire period, not a surface feature, but a global change. The data was clean, the change was real, and no one could explain it. Dr. Vasquez was interviewed by the ESO press office on September 20th. She chose her words carefully. "We have observed a spectral change in 3I Atlas that does not fit current models of cometry or asteroidal behaviour. The object's reflected light shifted from blue-white to red over a 3-day period, with no detectable change in temperature, rotation, or orbital position that would account for the shift. We do not have an explanation at this time." The interview was published on ESO's website on September 22nd. It was picked up by the Astronomy press within hours. Sky and Telescope ran a piece titled "Interstellar Object Changes Colour, Scientists Baffled." Space.com went with 3 Atlas defies explanation as surface colour, shifts without cause. The story was spreading, but it was also fragmented. The professional community was cautious. More data was needed. The amateur community was energised. Something unprecedented was happening. The press was caught between sober reporting and the temptation of mystery. Meanwhile, someone was looking at the trajectory again, and what they found made the colour change seem almost predictable by comparison. Sometimes the universe whispers, and sometimes it changes the rules just to see if you'll notice. Chapter 4. September 19th. The trajectory problem. Trajectories are supposed to be simple. An object approaches the Sun from interstellar space, travelling in a straight line at constant velocity. Gravity bends the path into a hyperbola, a smooth curve, symmetrical around the point of closest approach. The object swings around the Sun, accelerates slightly at perihelion due to the Sun's gravity, then exits in a new direction, still travelling in a straight line, still at constant velocity. Simple, predictable, deterministic. On September 19th, 2024, Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory published an updated trajectory analysis for 3I Atlas. The paper, uploaded to the preprint server archive, was titled "Orbital Dynamics and Origin Constraints for Interstellar Object 3I Atlas." The paper was dense, 18 pages of equations, orbital elements, gravitational simulations, and statistical analysis. But buried in section 4.3 was a paragraph that made several dynamicists stop and reread. The paragraph described 3I's encounter with Jupiter. On July 14th, 2024, 6 weeks before discovery, 3I Atlas passed within 0.3 astronomical units of Jupiter. That's 45 million kilometres. Close enough for Jupiter's gravity to measurably perturb the trajectory. Farnocchia's simulation showed that before the encounter, 3I's trajectory was aimed slightly inward toward the inner solar system. After the encounter, the trajectory was bent outward, sending the object on a path that would take it out of the solar system faster and at a steeper angle relative to the ecliptic, the plane where the planets orbit. In other words, Jupiter had altered 3I's path. Not enough to capture it, but enough to redirect it. This by itself is not unusual. Gravitational assists are common. NASA uses them routinely to send spacecraft to the outer planets. Voyager 1 and 2 used gravity assists at Jupiter and Saturn to reach escape velocity and leave the solar system. It's basic orbital mechanics. But here's the problem. 3I didn't choose to fly by Jupiter. It's a rock, or an iceberg, or whatever it is. It doesn't have engines. It doesn't navigate. And yet, statistically, the encounter was improbable. Farnocchia ran a Monte Carlo simulation, a statistical method where you generate thousands of random trajectories and see how many of them naturally result in a close encounter with Jupiter. He used the observed velocity and incoming direction of 3I, but randomized the precise trajectory within the uncertainty margins. Out of 20,000 simulated trajectories, only 11 passed within 0.5 AU of Jupiter. Only 3 passed within 0.3 AU. The odds of a random interstellar object threading that close to Jupiter, just by chance, are roughly 1 in 6,000 to 1 in 20,000, depending on the assumptions you make about the distribution of incoming velocities and angles. Low probability, not impossible, but low enough to make you pause. Farnocchia's paper didn't speculate, it simply reported the numbers. But in the discussion section, he included this line. The observed trajectory suggests either a statistically rare natural alignment or a trajectory influenced by factors not included in standard gravitational models. That phrase, factors not included in standard gravitational models, is about as close as a peer-reviewed paper gets to saying, we don't know what's going on. Dr. Darryl Seligman, a planetary scientist at the University of Chicago, read Farnokia's paper on September 20th. Seligman specializes in interstellar objects. He co-authored one of the early papers analyzing Oumuamua's trajectory, and was part of the team that identified its unexpected acceleration as it left the solar system. Oumuamua had its own trajectory problem. As it moved away from the Sun, it accelerated slightly. Not much, just a few %, but measurably. The acceleration wasn't consistent with gravity alone. Something was pushing it. The leading explanation was outgassing. As the object warmed near the Sun, ice sublimated, releasing gas that acted like a weak rocket thrust. It's the same mechanism that produces comet tails. But Oumuamua had no visible tail, no detectable coma. If it was outgassing, the effect was too small to observe directly, but large enough to measure in the trajectory. The explanation was plausible, but not conclusive, and it left questions. Seligman saw parallels with 3I, another interstellar object, another trajectory anomaly, but this time the anomaly wasn't acceleration, it was alignment. He reached out to Farnokia by email on September 21st. The subject line was simple: Jupiter flyby. Do we have enough data to rule out non-gravitational forces? Farnokia's reply was cautious. The orbit is well constrained by observations. Any non-gravitational force would need to be small, on the order of 10^8 AU per day squared, to avoid leaving residuals in the fit. But that's within the noise margin. We can't rule it out. We also can't confirm it. Seligman proposed a test. If 3I had used Jupiter's gravity to adjust its trajectory, not passively but actively, then the post-encounter trajectory should show an optimal alignment for some purpose. Maximum velocity increase, maximum deflection angle, minimum time to exit the solar system. Something. Seligman ran the numbers. The post-encounter trajectory showed a 4.7-degree deflection and a velocity increase of 1.2 kilometres per second. Both values were consistent with a natural gravity assist from a close flyby at that distance. But the outbound direction was interesting. After the Jupiter encounter, 3I's trajectory was aimed almost exactly perpendicular to the galactic plane, the flat disk of stars and gas that makes up the Milky Way. Most interstellar objects travel within a few degrees of the galactic plane, because that's where most stars are. Travelling perpendicular to the plane is unusual. It's not impossible. Some stars have orbits that take them high above or below the galactic plane. Objects ejected from those stars would naturally have perpendicular trajectories, but statistically it's rare. Seligman noted this in his analysis, but didn't draw any conclusions. The trajectory was perpendicular. That was a fact. Why it was perpendicular was speculation. On September 24th, Farnokia's paper was accepted for publication in the Astrophysical Journal Letters. The peer review was fast, only 5 days, because the paper was time-sensitive and the analysis was solid. The reviewers agreed with the findings. They also agreed that the Jupiter flyby was statistically unusual. One reviewer, whose identity is anonymized in the peer review system, included this comment in their report. The trajectory analysis is rigorous, and the conclusions are sound. However, I note that the authors avoid discussing potential non-natural explanations for the observed alignment. While I understand the hesitation, I believe the data warrants at least a brief mention of alternative hypotheses, if only to explicitly rule them out or identify what additional data would be needed to test them. Farnokia added a footnote to the discussion section in response. The footnote read, "While the observed trajectory is statistically rare, it remains consistent with natural processes and does not require the invocation of non-gravitational forces. Further observations of 3I's velocity and position over time will provide tighter constraints on any potential non-gravitational perturbations." The footnote was careful, precise. It said everything and nothing. By September 25th, the trajectory analysis was public. The press picked it up immediately. The headlines varied. Nature News went with, "Interstellar Objects Jupiter Flyby Raises Questions About Path." Scientific American ran, "Did 3I Atlas use Jupiter as a slingshot?" The SETI Institute issued a press release on September 26th, written by Dr. Frank Marcus. The release included a statement. The trajectory of 3I Atlas is unusual but not inexplicable. However, the combination of the close Jupiter encounter, the colour change, and the lack of cometary activity presents a pattern that deserves careful scrutiny. We are not suggesting artificial origin, but we are suggesting that 3I does not fit the standard profile of interstellar objects observed to date. That phrase, not suggesting artificial origin, was doing a lot of work. It was a way of acknowledging the question without asking it, a way of staying within the bounds of scientific conservatism while admitting that the bounds were being tested. The trajectory problem was now part of the 3I story. Not the biggest anomaly, not the strangest feature, but another piece in a growing puzzle. Sometimes the universe whispers, and sometimes it threads a needle through a gas giant just to see if you'll ask why. Chapter 5. September 26th. Starship's second orbital test. While astronomers were tracking an object they couldn't reach, engineers in Texas were building a rocket that might one day chase it. On September 26, 2024, SpaceX conducted the second full orbital test flight of its Starship vehicle, the largest, most powerful rocket ever built. The launch occurred at 0714 local time from the company's Starbase facility near Boca Chica, Texas. Starship is designed to be fully reusable. The first stage, called Super Heavy, stands 69 meters tall and is powered by 33 Raptor engines burning liquid methane and liquid oxygen. The second stage, Starship itself, is 50 meters tall, powered by 6 more Raptors, and designed to carry up to 100 tons of cargo to low, Earth orbit, or 21 tons to Mars. The first orbital test, conducted in April 2023, ended in a mid-air explosion 4 minutes after launch. The vehicle tumbled, lost control, and the automated flight termination system destroyed it. The failure was spectacular, but expected. First flights of new rockets rarely succeed. The second test was different. The Super Heavy booster lifted off cleanly, all 33 engines firing in synchrony, producing 17 million pounds of thrust. The sound was visceral, a sustained roar that could be heard 10 kilometres away, shaking windows and rattling equipment. At 2 minutes and 41 seconds into the flight, the booster completed its burn and separated from the upper stage. The separation was clean. The booster flipped using cold gas thrusters, ignited 13 of its engines for the boostback burn, and began its return to the launch site. At 8 minutes and 22 seconds, the booster descended toward the launch pad. This was the critical moment. Previous attempts at booster recovery had ended in explosions or crashes. SpaceX's Falcon 9 rocket had perfected the technique over years of iteration, but Falcon 9's booster is 1/3 the size of Super Heavy. At 50 meters altitude, the booster slowed to a hover. The engines throttled down. The vehicle descended gently, guided by GPS and radar. At 10 meters, 2 massive mechanical arms, called chopsticks, extended from the launch tower. At 7 seconds past 8 minutes, the arms caught the booster in midair, gripping it by the reinforced grid fins near the top. The landing was perfect. The first time in history a rocket of this size had been caught and recovered intact. At Mission Control in Hawthorne, California, the SpaceX team erupted in applause. Elon Musk, watching from the launch site, later posted on X, "The future is going to be incredible." Meanwhile, the upper stage continued its flight. It ignited its engines for the orbital insertion burn, reaching a velocity of 7.8 kilometers per second, orbital speed. The vehicle coasted for 40 minutes, completing 3/4 of an orbit, before re-entering the atmosphere over the Pacific Ocean. Re-entry is the hardest part. The vehicle hits the atmosphere at Mach 25, generating temperatures over 1,400 degrees Celsius. The heat shield, made of ceramic tiles bonded to a stainless steel skin, has to absorb and dissipate the energy without failing. The upper stage survived. It descended under control, deployed its flaps for stability, and ignited its engines one last time for the landing burn. At 200 meters altitude over the ocean, the engines cut off and the vehicle splashed down. Controlled re-entry, successful. The entire flight from liftoff to splashdown lasted 68 minutes. Both stages were recovered. Both could theoretically be refurbished and flown again. NASA issued a press release within hours. Congratulations to SpaceX on a successful test flight. Starship is a critical component of NASA's Artemis program, and our plans to return humans to the Moon. Today's success brings us one step closer to sustainable lunar exploration. Starship is contracted to serve as the lunar lander for Artemis 3, the mission that will put the first woman and the first person of colour on the Moon, currently scheduled for 2026. But Starship's ambitions go beyond the Moon. It's designed for Mars, for deep space, for missions that are currently impossible with existing rockets. One of those missions is Interstellar Object Intercept. On September 28th, Dr. Andreas Heen, a researcher at the Initiative for Interstellar Studies in London, published an analysis on the feasibility of sending a probe to intercept 3I Atlas before it leaves the solar system. The analysis was speculative, a thought experiment, not a mission proposal, but it laid out the numbers. 3I was currently 1.2 AU from the Sun, travelling at 33 kilometres per second. By February 2025, it would cross the heliopause at roughly 120 AU, the boundary where the solar wind from the Sun meets the interstellar medium. After that, it would be in true interstellar space, beyond the reach of solar-powered probes, beyond the practical limits of communication. To intercept 3I before it crossed the heliopause, a probe would need to launch by November 2024, 5 weeks away, and achieve a velocity of at least 40 kilometres per second relative to the Sun. That's faster than any human-made object has ever travelled. The fastest probe ever launched is Parker Solar Probe, which reached 163 kilometres per second at its closest approach to the Sun. But Parker achieved that speed by falling toward the Sun, using gravity to accelerate. To reach 40 kilometers outbound, away from the Sun, you need a different approach. Hein's analysis considered several options: nuclear electric propulsion, solar sails, gravity assists from Jupiter, and direct high-thrust chemical rockets. The most feasible option was a Starship launch, carrying a lightweight probe equipped with a nuclear thermal rocket, a propulsion system that heats hydrogen using a nuclear reactor, achieving exhaust velocities twice as high as chemical rockets. The mission would work like this. Starship launches the probe into a trajectory toward Jupiter. The probe uses Jupiter's gravity for a slingshot assist, gaining an additional 20 kilometers of velocity. After the flyby, the nuclear thermal engine ignites, adding another 15 kilometers. Total velocity, roughly 45 kilometers relative to the Sun. The probe would reach 3I in approximately 18 months, arriving before the object crosses the heliopause. Upon arrival, it would conduct a flyby. There's no way to slow down and match velocity with that much speed. Capturing high-resolution images, spectroscopy, and magnetic field data as it passes within a few hundred kilometers. The cost of such a mission, according to Hein's estimate, would be between $800 million and $1.2 billion. That's less than the cost of a Mars rover, less than the James Webb Space Telescope. But it's still a significant sum, and it would require approval, funding, and construction within 5 weeks. Not realistic, not with current timelines. But Hein's point wasn't that the mission was feasible. His point was that it was possible. The technology exists. The rocket exists. The only thing missing is the decision. In his conclusion, Hein wrote, 3I Atlas represents a unique scientific opportunity. If the object's anomalies are natural, they challenge our understanding of cometry and asteroidal processes. If they are not natural, the implications are profound. Either way, a close-up investigation is justified. The window for such a mission is narrow. We have the tools, we lack the will. The analysis was uploaded to ARCIV on September 28th. It was picked up by space news outlets within hours. The reaction was mixed. Some called it visionary, others called it premature, a few called it a waste of money, but the idea was out there. For the first time since Oumuamua, the question wasn't just, what is this object? It was, can we catch it? Sometimes the universe whispers, and sometimes we build the tools to shout back. We're not there yet, but we're getting closer. Chapter 6, October 3rd, The Tail that bent backwards. Comet tails are simple, predictable. They always point away from the Sun. That's because tails are made of dust and gas driven off the comet's nucleus by solar radiation and the solar wind. The radiation pressure, the physical force exerted by photons, pushes the dust away. The solar wind, a stream of charged particles flowing outward from the Sun, pushes the gas away. Both forces point directly away from the Sun, so the tail does too. There are exceptions. Ion tails can be bent slightly by the Sun's magnetic field, which rotates with the Sun, and creates a spiral pattern in the solar wind. But those bends are small, a few degrees at most, and they're always in the direction of the solar wind flow, never against it. On October 3, 2024, the Gemini South Telescope in Chile captured an image of 3I Atlas that broke that rule. The observation was part of a scheduled survey of outer solar system objects. The telescope's wide-field camera was imaging a patch of sky near the constellation Pisces, tracking several known asteroids and searching for new trans-Neptunian objects, the icy bodies beyond Neptune's orbit. 3I Atlas happened to be in the field of view. The image was processed automatically by the survey pipeline, software that aligns multiple exposures, subtracts background stars, and flags moving objects. On October 4th, a graduate student named Marcus Lowe was reviewing the flag detections when he noticed something odd about 3I. The object had a tail. Tails on interstellar objects are unusual but not unprecedented. 2I Borisov had a tail. It looked like a comet, acted like a comet, and had a normal dust tail pointing away from the sun. But 3I's tail was different. It was faint, barely visible above the background noise, but it was there, a diffuse streak extending roughly 40,000 kilometres from the nucleus. The direction was wrong. Lowe measured the tail's position angle relative to the sun's direction. A normal tail should point directly away from the sun, 180 degrees opposite the sun object line. 3I's tail was oriented at 169 degrees, an 11-degree deviation. Lowe thought it was an artifact, maybe a cosmic ray streak or a background star trailing due to imperfect tracking. He checked the raw images. The tail was present in all 5 exposures, taken over 2 hours. It wasn't an artifact. He checked the sun's position. His measurement was correct. The tail was bent 11 degrees off the expected direction. He emailed his supervisor, Dr. Sylvia Protopapa, a planetary scientist at the University of Maryland. Protopapa reviewed the images and the measurements. Her reply was short. Check photometry. If this is real, we need spectroscopy. Photometry confirmed it. The tail was real. It had a surface brightness about 15% above the sky background, consistent with scattered sunlight from dust particles. On October 6th, Gemini South was retasked for a spectroscopic follow-up. The goal was to measure the tail's composition, to see if it was dust, gas, or something else. The spectroscopy took 6 hours. The signal was weak but detectable. The tail's spectrum showed a smooth continuum. No emission lines, no absorption features. That's consistent with dust scattering sunlight. If the tail were made of gas, you'd expect emission lines from molecules like cyanogen, hydroxyl, or carbon monoxide, the typical gases released by comets. There were no emission lines, no gas, just dust. But here's the problem. If the tail is dust, it should point exactly away from the sun. Dust particles are pushed by radiation pressure, which acts in a straight line. The only way to bend a dust tail is with a force other than radiation pressure. One possibility is an ion tail, a tail made of ionized gas which can be deflected by magnetic fields. But 3I's tail showed no gas, no ions, just dust. Another possibility is outgassing from the nucleus, jets of gas escaping from the surface, carrying dust with them. If the jets are asymmetric, stronger on one side than the other, they can push the dust in a direction that's not perfectly anti-solar. This is seen in some comets, especially when they have active regions on their rotating nuclei. But 3I showed no outgassing, no coma, no gas emission lines in any of the previous spectroscopic observations. Dr. Protopapa ran simulations. She modelled different scenarios: rotating nucleus with asymmetric dust jets, non-gravitational forces from outgassing, interaction with the interplanetary magnetic field. None of the models could reproduce an 11-degree bend without also producing a detectable gas coma. On October 9th, she submitted a report to the Central Bureau for astronomical telegrams. The report included the images, the measurements, and a summary. Faint dust tail observed on 3 Atlas, oriented 11 degrees off anti-solar direction. No corresponding gas emission detected. Mechanism unknown. The report was published on October 10th. Within hours, it was being discussed on astronomy forums, Twitter, and Reddit. Dr. Andrei Koval, a planetary scientist at the Finnish Geophysical Institute, read the report and immediately thought of one more possibility: magnetic fields. Dust particles in space can become electrically charged due to ultraviolet light from the sun. Charged particles respond to magnetic fields. If 3I had a magnetic field, an internal field generated by the object itself, it could deflect charged dust particles, bending the tail away from the purely radial direction. But small objects don't have magnetic fields. Planets have them, because they have molten metallic cores where convection generates a dynamo. Some asteroids have remnant magnetism, frozen in fields from when they formed in a magnetized environment. But those fields are weak, and they don't change. For 3I to have a magnetic field strong enough to bend its dust tail, it would need an active dynamo. That would require a metallic core, internal heat, and convection. None of those are plausible for a small, inert interstellar object. Koval ran the calculations anyway. If 3I had a magnetic field of 10 microtesla, about 10% of Earth's surface field, and if the dust particles were charged to typical values by solar UV, the Lorentz force could deflect the particles by a few degrees over the time it takes them to travel 40,000 kilometres. But to deflect by 11 degrees, you'd need a field of at least 50 microtesla. That's as strong as Earth's field, for an object maybe 500 metres across. Impossible, or at least implausible. Koval wrote up his analysis and posted it on ARCIF on October 12th. The paper was titled Magnetic Deflection as a Possible Mechanism for the Anomalous Tail Orientation of 3I Atlas. In the conclusion, he wrote, "A magnetic field strong enough to explain the observed tail deflection would require an internal dynamo, which is not consistent with current models of small body interiors. Alternative explanations should be explored." By October 13th, the tail had become part of the growing list of anomalies: the colour change, the Jupiter flyby, the 11.7-hour photometric period, and now a tail that bent backwards. Each anomaly, by itself, had possible natural explanations. Each explanation required specific conditions. Unusual, but not impossible. But together, the anomalies were stacking up in ways that didn't fit a coherent picture. This is how science works. You gather data, you build models, you test the models against new data. When the models fail, you adjust them. When adjustments fail, you build new models. But sometimes the data doesn't fit any model, and that's when the quiet part starts to get loud. Sometimes the universe whispers, and sometimes it shows you a tail that defies physics, just to see if you'll keep watching. Chapter 7, October 10th. The hydrogen line radio astronomy is the art of listening to the universe. Stars emit radio waves, galaxies emit radio waves. Pulsars, rapidly rotating neutron stars, emit regular pulses of radio waves with such precision they were initially mistaken for alien signals. The universe is loud if you have the right ears. Small objects, asteroids, comets, interstellar visitors, are not supposed to emit radio waves. They're cold, inert, and magnetically dead. They can reflect radio waves if you bounce a signal off them, the way planetary radar works, but they don't emit on their own. On October 10th, 2024, the Very Large Array in New Mexico detected radio emission from 3I Atlas. The Very Large Array, VLA, is one of the most powerful radio telescopes in the world. There's actually 27 telescopes arranged in a Y-shaped configuration across the New Mexico desert, each dish 25 meters in diameter. By combining signals from all 27 dishes, the VLA can achieve the resolution of a single telescope 36 kilometers across. The VLA observes at frequencies from 1 GHz to 50 GHz, wavelengths from 30 centimeters to 6 millimeters. Different frequencies reveal different phenomena. Low frequencies show synchrotron radiation from supernova remnants and active galactic nuclei. High frequencies show thermal emission from dust and molecular clouds. One frequency is special, 1.42 GHz, 21 centimeters. The hydrogen line, neutral hydrogen, the most common element in the universe, has a hyperfine transition where the electron spin flips relative to the proton spin. The energy difference is tiny, but when billions of hydrogen atoms make the transition, they emit a photon at exactly 1.42 GHz. This frequency is everywhere. Interstellar clouds emit it. Galaxies emit it. It's the fundamental frequency of cosmic chemistry, and because it's so common, astronomers use it as a calibration standard. SETI, the Search for Extraterrestrial Intelligence, also watches the hydrogen line. The reasoning is simple. If an alien civilization wanted to send a signal that any technological species would recognize, they'd choose a frequency that's universally significant. The hydrogen line is the most obvious choice. it's nature's calling card. On October 10th, the VLA was conducting a survey of radio sources in the ecliptic plane, the region of sky where the planets orbit. The survey wasn't looking for 3I specifically, it was mapping the radio sky, cataloguing sources, and looking for transient events. 3I Atlas happened to be in the field of view. The data was processed automatically. The pipeline flags any detection above a certain signal-to-noise threshold and logs the position, frequency, and intensity. On October 12th, a postdoctoral researcher named Dr. Emily Reyes was reviewing the flagged sources when she noticed an entry labelled transient unidentified. The position matched 3I Atlas. The frequency was 1.42 GHz. The signal strength was weak, just 0.3 Janskis, barely above the noise floor, but it was there. Reyes thought it was interference. Radio telescopes are sensitive to all kinds of human-generated signals: satellites, aircraft, cell phones, even microwave ovens. The VLA has extensive radio frequency interference, RFI mitigation, but it's not perfect. She checked the RFI logs, no known sources. She checked the satellite tracking data, no satellites overhead at the time of observation. She checked the weather logs, clear skies, no thunderstorms, no ionospheric disturbances. The signal was real. She checked the observation logs for the previous week. The VLA had observed the same region of sky 3 times, on October 5th, October 8th, and October 10th. She pulled up the data from all 3 nights. The signal was present on all 3 nights. Same frequency, same position, same intensity within the noise margin, but it wasn't constant. It was pulsed. It appeared for about 40 minutes, then disappeared. Then appeared again 11.7 hours later. 11.7 hours. The same period as 3I's photometric variation. Reyes immediately emailed Dr. Anthony Remijan, a radio astronomer at the National Radio Astronomy Observatory, the organisation that operates the VLA. Subject line: possible radio detection from 3I Atlas. Need verification. Remijan reviewed the data remotely. His first thought was instrumental artifact. Radio detections of small solar system bodies are rare. Radio detections of interstellar objects are unheard of. The signal had to be something else. He requested a follow-up observation. On October 14th, the VLA pointed at 3I for a dedicated 6-hour window, covering half of the 11.7-hour period. The signal appeared right on schedule. At 02:34 UTC, the 1.42 GHz signal turned on. Intensity, 0.3 Janskis. Duration, 38 minutes. Then it disappeared. At 14:16 UTC, 11.7 hours later, it appeared again. Same frequency, same intensity, same duration. The detection was confirmed. Remijan ran every diagnostic he could think of. He checked for Doppler shifts that would indicate the signal was coming from Earth. None. He checked for polarization patterns that would indicate reflection or scattering. None. He checked for bandwidth. The signal was narrow, just a few kilohertz wide, centered exactly on 1.42945 GHz. By October 16th, Remijan was convinced the signal was real, but he was also convinced it couldn't be real. Small objects don't emit radio waves, certainly not at the hydrogen line, certainly not in a repeating pattern. He reached out to colleagues at the Arecibo Observatory in Puerto Rico asking if they could confirm the detection. Arecibo had the sensitivity, but it was undergoing maintenance and wouldn't be available until November. He reached out to the Parkes Observatory in Australia. Parkes confirmed they could observe 3I, but the object was only visible for a few hours per night due to its position in the sky. They scheduled observations for October 18th and October 20th. Parkes detected the signal on both nights. Same frequency, same 11.7-hour period, independent confirmation. By October 21st, 3 observatories had confirmed the signal. It was real. It was coming from 3I, and no one could explain it. The discovery was leaked to the press before peer review. On October 22nd, a journalist at New Scientist received an anonymous email containing the VLA data and a brief summary. The email was titled "Interstellar Object Emitting Radio Signals, Not a Hoax." The journalist, Emma Davies, contacted Remijan for comment. Remijan declined to confirm the specifics, citing ongoing analysis, but acknowledged that anomalous radio emission has been detected in the vicinity of 3I Atlas and is under investigation. That was enough. The story broke on October 23rd. The headline, Interstellar Visitor 3I Atlas emitting radio signals at hydrogen line frequency. The reaction was immediate. Twitter exploded. Reddit's r/space hit the front page. The SETI Institute issued a statement within hours. We are aware of the reports regarding radio emission from 3I Atlas. While the detection is intriguing, it is premature to speculate on the cause. Natural phenomena, including pulsars, magnetars, and background sources, can produce emission at 1.42 GHz. We urge caution and await peer-reviewed analysis. But the statement couldn't contain the speculation. The hydrogen line, the 11.7-hour period, the timing that matched the photometric variation, it was too much. Dr. Avi Loeb, the Harvard astronomer who famously suggested Oumuamua might be artificial, was contacted by multiple news outlets for comment. His response, published in The Guardian on October 24th, was measured but suggestive. The hydrogen line is a natural frequency, and natural processes can produce emission at that frequency. However, the periodic nature of the signal, combined with the other anomalies observed in 3I Atlas, warrants serious investigation. We should not dismiss the possibility of a technological origin without thoroughly ruling out all natural explanations first. That phrase, technological origin, was now in the public conversation, not as a conclusion, but as a question that couldn't be ignored. By October 25th, NASA issued a statement. It was brief, careful, and non-committal. NASA is aware of recent reports regarding radio emission detected near the trajectory of 3I Atlas. We are coordinating with international partners to conduct follow-up observations and analysis. At this time, there is insufficient data to determine the source or nature of the emission. We will provide updates as more information becomes available. The signal was real, the implications were staggering, and the universe was still whispering, but now the whisper had a frequency. 1.42 GHz, the hydrogen line, nature's calling card, or someone else's. Sometimes the universe whispers, and sometimes it uses the one frequency we're all listening to. Chapter 8, October 18th. The silence from headquarters. Science is supposed to be open, transparent, a collective endeavour where data is shared, hypotheses are tested, and conclusions are debated in public. But when the data is strange enough, when the implications are big enough, institutions go quiet. On October 18, 2024, NASA's Jet Propulsion Laboratory held an internal briefing on 3I Atlas. The meeting was not announced publicly, no agenda was published, no minutes were released afterward. We know the meeting happened because 3 attendees confirmed it in later interviews, and because calendar invitations were visible in shared scheduling systems used by JPL staff. The attendees included Dr. Davide Farnocchia, the trajectory analyst who had calculated the Jupiter flyby odds, Dr. Linley Johnson, head of the Planetary Defense Coordination Office, Dr. Thomas Zurbuchen, former Associate Administrator for NASA's Science Mission Directorate, now consulting on interstellar object research, Dr. Pamela Gay, an astronomer and science communicator who had been publicly discussing 3I on social media, and at least 7 others whose names were redacted from the calendar invites. The meeting lasted 2 hours. No press release followed. 1 week later, on October 25th, the European Space Agency held a closed-door session with member state representatives. The session was part of ESA's Science Programme Committee meeting, held at ESA headquarters in Paris. The agenda listed Item 7.3, Status Update on Interstellar Object 3I Atlas. No minutes were published. No public statement was issued. We know the session happened because ESA's public calendar listed it, and because a leaked internal memo circulated among member state delegations referenced ongoing coordination with NASA regarding observational priorities and potential mission concepts for interstellar object investigation. This is how institutions handle uncertainty. They don't lie. They don't fabricate. They just go quiet. They delay. They wait for more data, more confirmation, more clarity before making public statements. The strategy is understandable. The memory of Oumuamua is still fresh. When Oumuamua was discovered in 2017, the scientific community was excited but cautious. The object was unusual, elongated, tumbling, with an unexpected acceleration that suggested outgassing but no visible coma. The data was ambiguous. Then Dr. Avi Loeb published a paper suggesting that Oumuamua's properties were consistent with a light sail, a thin, reflective sheet pushed by sunlight, a technology that humans have considered for interstellar travel. He didn't claim it was artificial. He simply stated that the hypothesis couldn't be ruled out with available data. The media response was explosive. Headlines range from Harvard scientist says Oumuamua could be alien spacecraft to interstellar visitor may be probe from extraterrestrial civilization. The nuance was lost. The speculation dominated. The scientific community pushed back hard. Dozens of papers were published offering natural explanations for Oumuamua's acceleration, outgassing of hydrogen, nitrogen ice sublimation, fractal ice structures. Some of the explanations were plausible, some were not. But the message was clear. Extraordinary claims require extraordinary evidence, and we didn't have it. Loeb stood by his hypothesis. He argued that dismissing the possibility of technology without investigation was unscientific. The debate became polarized. Loeb was labelled a sensationalist by some, a courageous thinker by others. The controversy left scars. Institutions became more conservative. Public statements became more guarded. The fear of being associated with speculation, of being the next Loeb, made scientists hesitant to discuss anything that sounded even remotely like alien technology. And now here was 3 Atlas, an object with a colour change, a Jupiter flyby, a hydrogen line signal, a backwards bending tail, a photometric period that matched the radio period. Each anomaly had possible natural explanations, but the combination was harder to explain. And the longer the institution stayed silent, the louder the public speculation became. Dr. Pamela Gay, who had attended the JPL briefing, later spoke about it in a podcast interview on November 2nd. She was careful not to disclose confidential details, but she described the tone of the meeting. There's a tension between wanting to be open and transparent and not wanting to fuel speculation without sufficient data. Everyone in that room knew the data was strange. Everyone also knew that strange data doesn't always mean strange conclusions. Sometimes it just means we're missing something. But when you have multiple independent anomalies, all pointing in the same weird direction, you have to take it seriously, and taking it seriously means talking about it. The question is how to talk about it responsibly. That question, how to talk about it, was dividing the community. Some argued for full transparency, release all the data, let the public see the anomalies, let independent researchers contribute, crowdsource the analysis. Science thrives on open collaboration. Others argued for caution. Wait until the analysis is complete. Wait until peer review is finished. Avoid sensationalism. Protect the credibility of the institutions. Don't repeat the Oumuamua circus. The debate was happening in private emails, in closed meetings, in conversations that never made it into the public record. Meanwhile, outside the institutions, the investigation was continuing without official approval. Amateur astronomers kept tracking 3I. The Unistellar network logged observations every clear night. Koirama Observatory in Chile captured photometry. Kleinkaroo in South Africa captured spectra. The data was uploaded to open repositories, GitHub, Zenodo, the Minor Planet Center's database. Citizen scientists analysed the data. They wrote Python scripts to model the light curves. They cross-referenced the radio detections with the photometric periods. They built simulations of the trajectory, tested different compositional models, calculated statistical probabilities. The investigation was distributed, decentralized. No single institution controlled it. On October 27th, a Discord server called 3i Watch was created by a software engineer named Alex Huang. The server was open to anyone interested in 3 Atlas. Within 48 hours, it had 200 members, amateur astronomers, graduate students, retired scientists, curious enthusiasts, and a handful of professional astronomers participating unofficially. The server had channels for observations, data analysis, literature review, and speculation. The speculation channel had a pinned message. This channel is for hypothesis generation, not conclusions. Be creative, be rigorous, be respectful. No conspiracy theories, no pseudoscience, evidence-based speculation only. The community was self-policing. When someone posted a claim without data, others asked for sources. When someone proposed a model, others tested it against the observations. The culture was skeptical but open. One member, using the handle Stardust407, posted a statistical analysis on October 29th. The post calculated the joint probability of three eyes observed anomalies occurring by chance, hyperbolic trajectory through Jupiter's gravity well within 0.3 AU, 1 in 20,000, hydrogen line radio emission with 11.7-hour periodicity, 1 in 5,000, assuming instrumental false positives are excluded, colour change from blue-white to amber-red without thermal cause, 1 in 10,000, based on known material properties. Dust tail bent 11 degrees off anti-solar direction with no detectable gas, 1 in 2,000. Coherent spectroscopic features suggesting both organic compounds and metallic oxides, 1 in 8,000. Combined probability, assuming independence of events, roughly 1 in 8 trillion. The analysis included caveats. The probabilities were rough estimates, not rigorous calculations. The assumption of independence might not hold, but the point was clear. Even with generous error margins, the odds were astronomical. The post was pinned in the data analysis channel. Within hours, it had been reviewed, critiqued, and refined by other members. The final consensus probability, after adjustments, was somewhere between 1 in 1 trillion and 1 in 20 trillion. Low probability, high impact. The silence from official institutions was becoming conspicuous. The absence of statements was itself a statement, and the public was noticing. On October 30th, a reporter from the New York Times submitted a Freedom of Information Act (FOIA) request to NASA, asking for all internal communications, briefing documents, and meeting notes related to 3A Atlas. NASA's response, issued on November 3rd, acknowledged the request and stated that processing would take approximately 90 to 120 days due to the volume of records and the need to review for sensitive or classified information. 90 to 120 days. By then 3I would be gone. Sometimes the universe whispers, and sometimes the people who hear it go quiet, hoping the whisper fades before anyone else notices. It didn't fade. Expanded script. Chapter 9, October 25th. Perseverance finds organic signatures on Mars. While astronomers were debating an interstellar object they couldn't reach, a rover on Mars was quietly rewriting the story of life's building blocks. On October 25, 2024, NASA announced that the Perseverance rover had detected organic molecules in a rock sample collected from Jezero Crater, a 45-kilometre-wide impact basin that once held a lake, billions of years ago when Mars had liquid water on its surface. The rock was named Shenandoah Ridge. Perseverance had drilled into it on August 17th, using its coring drill to extract a cylindrical sample about the size of a stick of chalk. The sample was analysed on the rover itself using two instruments: Sherlock, scanning habitable environments with Raman luminescence for organics and chemicals, and Pixel, planetary instrument for X-ray lithochemistry. Sherlock uses ultraviolet laser spectroscopy to identify organic molecules. When the laser hits organic compounds, they fluoresce. They absorb the UV light and re-emit it at longer wavelengths. The pattern of fluorescence is like a fingerprint, identifying specific molecular structures. Pixel uses X-ray fluorescence to map the elemental composition of rocks: carbon, nitrogen, oxygen, sulfur, phosphorus, the elements essential for life. The data from both instruments showed clear signatures of organic molecules, specifically polycyclic aromatic hydrocarbons, PAHs, complex ring-shaped molecules made of carbon and hydrogen. PAHs are not life, but they're the building blocks of life. They form naturally in space, in interstellar clouds, in the atmospheres of dying stars, in the dusty disks around young stars where planets form. They're also produced by biological processes, by the breakdown of organic matter, by chemistry that happens in the presence of life. Finding PAHs on Mars isn't proof of life, it's proof that the chemistry necessary for life was present, that the ingredients were there, that if life emerged on Mars it had the raw materials. Dr. Sunanda Sharma, a planetary scientist at JPL and a member of the Perseverance science team, spoke at the press conference on October 25th. Her tone was measured but excited. What we're seeing in Shenandoah Ridge is a rich organic signature, preserved in a rock that formed in an aqueous environment, a lake or river delta, roughly 3.5 billion years ago. The PAHs we've detected are consistent with both abiotic processes, chemistry, that happens without life, and biotic processes, chemistry that happens because of life. We can't distinguish between those two possibilities with the instruments on Perseverance. To do that, we need to bring the samples back to Earth. That last sentence is key. Perseverance is collecting samples and sealing them in tubes, leaving them on the Martian surface for a future mission to retrieve. The Mars Sample Return Mission, a collaboration between NASA and ESA, is designed to land on Mars, collect the tubes, launch them into orbit, and bring them back to Earth for analysis in laboratories far more sophisticated than anything that can be sent to Mars. The timeline for sample return is uncertain. Current plans target the early 2030s, but budget constraints and technical challenges have delayed the mission multiple times. Still, the detection of organics is significant. It's the strongest evidence yet that Mars once had the conditions for life, not just water, not just the right temperature, but the chemistry, the molecules. The announcement was front-page news. The New York Times ran, "Mars rover finds organic molecules in ancient lake bed." The BBC went with "Building blocks of life detected on Mars." The story was hopeful, exciting, and grounded in solid science. But there was a thematic resonance, a parallel. We search for life by looking for chemistry, for patterns, for signatures that don't quite fit the expected background. We use spectroscopy. We measure wavelengths. We look for molecules that shouldn't be there, or that appear in ratios that suggest something more than random geology. The same tools we use on Mars, spectroscopy, isotope analysis, elemental mapping, are the tools we're using on 3I Atlas. On Mars we found PATs. On 3I we found PAS 2, along with metallic oxides, silicon carbide, and a spectral signature that didn't fit any known natural process. On Mars, we found patterns in the mineralogy that suggest water, life, and chemistry. On 3I, we found patterns in the trajectory, the radio signal, and the color change that suggest what? Dr. Avi Loeb made the connection explicit in an op-ed published in Scientific American on October 28th. The piece was titled, "What Mars and 3I Atlas Have in Common." In the article, Loeb wrote, "When we search for life, we search for anomalies, for chemistry that deviates from the baseline, for structures that require explanation. Perseverance found organics on Mars, and we celebrate that as a step toward answering one of humanity's oldest questions. Are we alone? But when we find anomalies in an interstellar object, anomalies that defy natural explanation with the same rigor we apply to Mars, we hesitate. We demand higher standards of proof. We invoke conservatism. Why? Because the implications are uncomfortable. Because the question is not just, are we alone, but is someone else here, watching us? The data from 3I Atlas deserves the same scrutiny, the same openness, the same intellectual courage that we apply to Mars. If we're willing to search for life in the chemistry of ancient rocks, we should be willing to search for it, or for technology, in the behavior of interstellar visitors. The op-ed was widely shared. It was also widely criticized. Some called it premature, others called it irresponsible. A few called it exactly what science needed, a willingness to ask uncomfortable questions. The debate was no longer just about 3I. It was about how we do science, how we balance skepticism and openness, how we handle data that doesn't fit the models. Meanwhile, on Mars, Perseverance continued its mission. On October 29th, the rover collected another sample, this time from a rock called Isola Ridge. Initial analysis showed more organics, more PAS. The chemistry was consistent, the pattern was holding, and 2,000 astronomical units away, give or take, 3I Atlas continued its journey outward, fading, receding, carrying its own pattern of anomalies toward the heliopause. 2 objects, 2 mysteries, 1 question. Sometimes the universe whispers, and sometimes it speaks in the language of chemistry, on a dead planet and in the light from a distant visitor. We're listening to both. We just don't know what they're saying yet. Chapter 10. November the 2nd. The albedo spike. Albedo is a measure of reflectivity. 0 is perfectly black, absorbing all light. 1 is perfectly reflective, like a mirror. Most asteroids have albedos between rule of 5 and 0.25, dark to moderately bright. 3I Atlas had an albedo of about 0.0, dark, consistent with a carbonaceous surface, or heavily weathered rock. Albedo shouldn't change. Not quickly, not without a reason. On November 2nd, 2024, the Hubble Space Telescope finally locked onto 3i Atlas for its long-awaited observation window. The observation had been approved on October 20th, after the NASA budget review concluded and emergency telescope time was granted. But scheduling took time. Hubble's orbit, its pointing constraints, and the need to coordinate with other ongoing observations meant the earliest available window was November 2nd through November 4th, a 48-hour block. By this time, 3i was magnitude 22, faint, at the edge of Hubble's sensitivity for detailed photometry, but still observable. The observation plan was straightforward. Continuous photometry over 48 hours, covering 4 full rotations of the 11.7-hour period. The goal was to capture a detailed light curve, a graph of brightness versus time, to look for variations that might reveal surface features, rotation rate changes, or anything else unusual. Hubble's Advanced Camera for Surveys, ACS, was used. ACS is optimized for high-resolution imaging in visible wavelengths. It's the instrument that captured the iconic Hubble Deep Field images, the ones showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. For 3i, the resolution was less important than the sensitivity. The object was small, distant, and faint. Every photon counted. The data was transmitted to the Space Telescope Science Institute in Baltimore for processing. By November 5th, the light curve was ready. Dr. Susan Benecke, a planetary astronomer at the Planetary Science Institute, was part of the Hubble observation team. She reviewed the light curve on the morning of November 6th. The curve showed the expected 11.7-hour periodicity. Brightness increasing and decreasing as the object rotated and different surfaces faced the telescope. But there was something else. At hour 23 of the observation, about halfway through the second rotation, the brightness spiked. Not gradually, not smoothly. It jumped by 0.4 magnitudes in less than 30 minutes, then decayed back to baseline over the next 4 hours. A magnitude change of 0.4 corresponds to a 40% increase in brightness. For context, that's like a surface going from charcoal dark to concrete grey in half an hour. Benecke thought it was an instrumental glitch. She checked the raw data. No glitches. She checked the calibration. No errors. She checked for cosmic ray hits, high-energy particles that can strike the detector and create false signals. No hits in that time window. The spike was real. She compared the spike to the photometry from the first rotation. No corresponding spike. The first rotation was smooth, consistent with a rotating object with a heterogeneous surface. The spike occurred only during the second rotation, and then, during the third and fourth rotations, it didn't appear again. On November 7th, Benecke convened a teleconference with the observation team. The group included experts in photometry, surface science, and small body dynamics. They reviewed the data together. The consensus was that the spike was real, but the cause was unclear. Several hypotheses were proposed: outgassing event, a sudden release of gas from the surface, carrying dust that increased the reflectivity temporarily. But spectroscopy from ground-based telescopes during the same time window showed no gas emission lines. Impact event, a micrometeorite striking the surface, excavating fresh material that's more reflective than the weathered exterior. Possible, but the decay time, 4 hours, seemed too long for an impact plume to dissipate. Surface fracture, thermal stress causing a crack to open, exposing subsurface ice or fresh rock. But 3i was moving away from the sun, cooling, not heating. Thermal stress should decrease, not increase. Rotation-induced feature, a highly reflective patch rotating into view, then rotating out. But the spike occurred only once in 4 rotations. If it were a surface feature, it should appear every rotation. None of the hypotheses fit perfectly. Dr. Paul Chodas, the director of NASA's Center for Near-Earth Object Studies, reviewed the data on November 9th. In an internal email to the observation team, he wrote, "The albedo spike is inconsistent with any natural process I'm aware of. It's as if a section of the surface became temporarily more reflective, then returned to normal. I don't have a model for that." On November 10th, the Hubble data was uploaded to the Mikulski Archive for Space Telescopes, the public repository for all Hubble observations. The data was immediately downloaded by researchers around the world. Within 24 hours, 2 independent teams had confirmed Benecki's findings. The spike was there. The timing was correct. The magnitude change was 0.4. Within 48 hours, a preprint was posted on Archive by Dr. Michelle Bannister and her team at the University of Canterbury. The paper was titled Transient Albedo Increase in Interstellar Object 3I Atlas, Observations and Implications. The paper included the Hubble light curve, the ground-based spectroscopy showing no gas emission, and a detailed discussion of possible mechanisms. The conclusion was cautious. The observed albedo spike cannot be explained by standard models of cometry or asteroidal activity. The absence of corresponding gas emission rules out outgassing. The timing and duration rule out impact or rotational features. We propose that the event may represent a previously unobserved surface process, possibly related to the object's interstellar origin. Further observations are urgently needed. The paper didn't say, "We don't know," but it came close. By November 12th, the albedo spike was being discussed alongside the other anomalies: the colour change, the trajectory, the radio signal, the backwards tail, and now a brightness spike that lasted 4 hours and never repeated. The cumulative improbability was growing. Each anomaly by itself could be explained with enough creativity. But the combination was harder to dismiss. Dr. Frank Marchis from the SETI Institute posted a thread on X, formerly Twitter, on November 13th. The thread read, "Let's be clear about what we're seeing with 3I Atlas. Each anomaly has a possible natural explanation. Emphasis on possible. But let's list them. Colour change, unknown material process. Jupiter flyby, 1 in 20,000 coincidence. Radio signal, unknown emission mechanism. Backwards tail, unknown force. Albedo spike, unknown surface event." At some point, unknown stops being a scientific explanation and starts being a pattern. I'm not saying it's artificial. I'm saying we should be open to testing that hypothesis rigorously instead of dismissing it reflexively. The thread was retweeted 14,000 times. It was quoted in news articles. It was debated in academic forums, and it marked a shift. The conversation was no longer just what is 3I, it was what if 3I isn't natural? That question was uncomfortable. It violated norms. It invited speculation. But it was also increasingly unavoidable. Sometimes the universe whispers, and sometimes it flashes at you for 4 hours, just long enough to make you wonder if it's waving. Chapter 11, November 10th. The composition that doesn't fit. Chemistry tells stories. The elements in a rock, the isotopes in a molecule, the ratios of carbon to nitrogen to oxygen. All of these reveal where an object came from, how it formed, what environment shaped it. Asteroids in the main belt between Mars and Jupiter have compositions that match the solar nebula, the disk of gas and dust from which the Sun and planets formed 4.6 billion years ago. Comets from the Kuiper belt have ices and organics that formed in the cold outer regions of that same nebula. Meteorites that fall to Earth carry signatures of their parent bodies. We can trace them back to specific asteroids, sometimes even to specific regions of those asteroids. Chemistry is a forensic tool. It tells us the history of the universe, one atom at a time. On November 10th, 2024, the W.M. Keck Observatory in Hawaii released a detailed spectroscopic analysis of 3I Atlas, conducted over 5 nights in late October and early November. The observations used the HIRES spectrograph, high-resolution Shell spectrometer, capable of resolving spectral features to within 0.01 nanometers. That's precise enough to distinguish between isotopes of the same element based on tiny shifts in their absorption lines. The data was analysed by Dr. Yuki Tanaka, a cosmochemist at the Tokyo Institute of Technology. Tanaka specialises in the composition of small solar system bodies and interstellar dust. She's analysed spectra from dozens of asteroids, comets and meteorites. The spectrum of 3I Atlas was unlike anything she'd seen. The most prominent features were absorption lines consistent with polycyclic aromatic hydrocarbons, PAHs. These are large, complex organic molecules made of carbon and hydrogen arranged in interconnected rings. PAHs are common in space. They form in the atmospheres of dying stars, in interstellar clouds, in protoplanetary disks. They've been detected in meteorites, in comets, in the diffuse dust between stars. Finding PAHs on 3I wasn't surprising. It confirmed earlier observations from the Very Large Telescope, but there were other features. absorption lines at 9.7 micrometers, consistent with silicate dust, the same material that makes up rocky planets and asteroids. Absorption lines at 11.3 micrometers, consistent with silicon carbide, a refractory compound that forms in the hot, oxygen-poor environments around carbon-rich stars, and emission features at 3.3 and 6.2 micrometers, consistent with metallic oxides, possibly iron oxide or aluminum oxide. The combination was geologically incoherent. PAS form in cold environments. Silicon carbide forms in hot environments. Silicates are common in rocky bodies. Metallic oxides are rare except in differentiated bodies, objects that were once molten, allowing metals to sink to the core and oxides to concentrate in the mantle. 3I was small, maybe 500 meters across based on brightness and assumed albedo. Too small to have ever been, molten. Too small to differentiate into core, mantle and crust. And yet the spectrum suggested materials from incompatible environments. Cold interstellar clouds, hot stellar atmospheres, and differentiated planetary interiors. Tanaka ran models. She tried to construct a scenario where all these materials could coexist naturally. One possibility: 3I is a fragment of a larger body that did differentiate, then shattered in a collision. The fragment carried pieces of the core, metals, the mantle, oxides, and the surface, PETs deposited from interstellar dust. Possible. But fragments from differentiated bodies have specific compositional patterns, and 3I's pattern didn't match. Another possibility: 3I is a rubble pile, a loose aggregate of different materials swept together over millions of years as the object drifted through interstellar space, accreting dust grains from different environments. Possible. But rubble piles are fragile. The tidal forces during the Jupiter flyby should have disrupted it. A third possibility: 3I is artificial, a composite material, engineered from different sources for different purposes, metals for structure, organics for surface coating, silicates for thermal protection. Tanaka didn't include the third possibility in her analysis, not because it was impossible, because it was unpublishable without extraordinary evidence. Instead, her paper, submitted to the Astrophysical Journal on November 12th, concluded: the observed spectral features of 3I Atlas are inconsistent with any single formation environment. The coexistence of pH, silicon carbide, silicates, and metallic oxides suggests either a complex collisional history, a unique interstellar accretion process, or a compositional origin not accounted for in current models. Further observations, particularly in the mid-infrared, are needed to constrain the relative abundances and spatial distribution of these materials. The paper was carefully worded. It said, inconsistent with current models. It didn't say impossible, it didn't say artificial. But the implication was there, hovering just below the text. Dr. Andrew Rivkin, a planetary scientist at Johns Hopkins Applied Physics Laboratory, reviewed the paper as part of the journal's peer review process. His comments, later shared in a conference presentation, were blunt. This is not a composition that forms naturally in a protoplanetary disk. I don't know what it is. But it's not a normal asteroid. It's not a normal comet. It's something else. The paper was accepted for publication on November 18th. It was published online on November 20th. The press reaction was immediate. Sky and Telescope ran a piece titled, 3I Atlas's composition defies explanation. Space.com went with Interstellar Visitor contains materials that don't belong together. Dr. Avi Loeb, predictably, was asked for comment. His response, published in a blog post on November 21st, was direct. The composition of 3I Atlas is a smoking gun. Not proof, but evidence that demands explanation. If this object is natural, it challenges everything we know about planetary formation and interstellar chemistry. If it's not natural, it challenges everything we know about our place in the universe. Either way, it's the most important object in the sky right now, and we're letting it slip away. By November 22nd, the composition analysis was part of the public record. PATES, silicon carbide silicates, metallic oxides, a chemistry set that didn't belong. It was like finding a forest growing inside a foundry. Not impossible, technically, just implausible, incoherent, wrong. And the wrongness was stacking up. One anomaly after another, each one strange but explainable, until the explanations themselves became more implausible than the alternative. Sometimes the universe whispers, and sometimes it hands you a chemistry set that doesn't fit any recipe you've ever seen. Chapter 12. November 18th. The model that almost worked. Science loves a good explanation. Not a perfect explanation. Those are rare. But a good explanation. One that accounts for most of the data, fits within known physics, and doesn't require invoking entirely new phenomena. On November 18th, 2024, a team at MIT published a preprint that offered exactly that. The paper was titled A Fractal Ice Model for the Anomalous Behavior of Interstellar Object 3I Atlas. The lead author was Dr. Terence Zhao, a planetary scientist specializing in cometary physics and non-equilibrium thermodynamics. The model was elegant. It proposed that 3I was composed primarily of water ice, but not ordinary crystalline ice. Instead, the ice had a fractal structure, a porous sponge-like arrangement where ice molecules formed branching networks with enormous surface area packed into a small volume. Fractal ice is rare but not unknown. It's been created in laboratories under specific conditions, rapid freezing, low temperatures, high vacuum. It's thought to exist in the outer solar system, in the coldest comets that never approached a star closely enough to restructure their ice into crystalline form. Zhao's model proposed that 3I's ice was laced with metallic dust, tiny grains of iron, nickel, and silicates, trapped within the fractal structure during formation. The dust would give the object a dark, rocky appearance, explaining the low albedo and the absence of a visible coma. The key insight was that fractal ice undergoes non-thermal phase transitions when exposed to cosmic rays. High-energy particles, protons and heavy nuclei from supernovae and galactic processes continuously bombard objects in interstellar space. When a cosmic ray hits fractal ice, it deposits energy locally, causing structural rearrangements without raising the bulk temperature. These rearrangements could explain the color change. As the ice structure shifted, the metallic dust embedded within it would be exposed or buried, changing the surface. Reflectivity. A shift from blue-white, metallic dust exposed, to amber-red, organic coating exposed, could occur without any change in temperature. The model also explained the backwards bending tail. If the fractal ice released gas intermittently, not through thermal sublimation, but through sudden structural collapses triggered by cosmic ray hits, the gas jets could be asymmetric and transient, producing a tail that didn't align perfectly with the sun's direction. The albedo spike. Another structural collapse temporarily exposing a fresh reflective ice surface before it darkened again due to radiation damage. The hydrogen line radio emission was harder to fit, but Zhao proposed a mechanism. Metallic dust grains, charged by ultraviolet light, could oscillate in response to the object's rotation, producing weak electromagnetic radiation. If the dust distribution had the right geometry, the emission could peak at the hydrogen line frequency by coincidence. The Jupiter trajectory? Coincidence. Low probability, but not zero. The model was mathematically rigorous. It included simulations, thermodynamic calculations, and predictions for future observations. It accounted for 4 of the 5 major anomalies without invoking anything beyond known physics and chemistry. The scientific community exhaled. The paper was posted on Astronomy on November 18th. Within 48 hours, it had been downloaded over 5,000 times. Within a week, it had been cited in 3 follow-up papers and discussed in a dozen blog posts. The media ran with it. The headline in Nature News was "Natural Explanation for Interstellar Objects' Odd Behavior." Scientific American went with MIT team solves the 3I Atlas puzzle. The relief was palpable. We didn't need to invoke the exotic. We didn't need to talk about technology. We had a model, a good model, one that fit the data, except it didn't. On November 22nd, the Atacama Large Millimeter Array, ALMA, in Chile, completed a scheduled observation of 3I Atlas. ALMA is the most powerful radio telescope in the world for observing coal dust and gas. It's designed to detect emission from molecules in space, particularly at millimeter and sub-millimeter wavelengths, where cold material radiates. If 3I was made of fractal ice, ALMA should detect it. ICE emits thermal radiation in the millimeter range. The emission is faint, but detectable, and fractal ice, with its enormous surface area, should emit more strongly than regular crystalline ice. The observation lasted 12 hours. The data was processed on November 24th. no detection. ALMA's sensitivity was more than sufficient to detect ice at 3 eyes distance, even for a small object. The upper limit on the ice emission was 3 orders of magnitude below what Zhao's model predicted. In other words, if 3I was made of fractal ice, ALMA would have seen it. ALMA saw nothing. Dr. Zhao was contacted by email on November 25th by Dr. Stephanie Millam, a planetary scientist at NASA's Goddard Space Flight Center and part of the ALMA observation team. The email was brief. We've completed the ALMA observations of 3I. No sub-millimeter emission detected. The upper limit rules out fractal ice as the dominant component. Thought you'd want to know. Zhao's response: thank you for sharing. I need to revisit the model. On November 27th, Zhao posted an update to the ARXIV preprint. The update included a new section titled Constraints from ALMA Observations. The text read, recent submillimeter observations by ALMA place stringent upper limits on the ice content of 3I Atlas. These limits are inconsistent with the fractal ice model as presented. Either the ice fraction is much lower than assumed, or the model requires fundamental revision. We are exploring alternative scenarios. The model had collapsed. The scientific community deflated. The media ran follow-up stories. Nature News updated their headline to Interstellar Object Puzzle Deepens as Natural Model Fails. Scientific American went with back to the drawing board for 3I Atlas. It wasn't the first time a model had failed. Science is full of failed models. That's how progress happens. You propose an explanation, you test it. If it doesn't fit, you discard it and try again. But this felt different. The fractal ice model wasn't just wrong. It was the best natural explanation anyone had come up with. It was elegant, plausible, and grounded in known physics, and it failed. What did that leave? Dr. Sarah Seeger, an astrophysicist at MIT and one of Zhao's co-authors, spoke about the model's failure in an interview with The Guardian on November 29th. She said, when your best natural model doesn't work, you have 2 options. You can try to build a better natural model, or you can start considering unnatural models. I'm not ready to give up on natural explanations yet, but I'm also not willing to dismiss other possibilities just because they're uncomfortable. That word, unnatural, was a euphemism. Everyone knew what it meant. By November 30th, the conversation had shifted. It was no longer, here's the explanation. It was, we don't have an explanation. And in the absence of explanation, speculation filled the void. Sometimes the universe whispers, and sometimes it breaks the best model you can build just to see what you'll try next. Expanded script. Chapter 13, November the 27th. The odds. We can't ignore. Statistics is the language of uncertainty. When we can't measure something directly, we estimate probabilities. When we can't explain something completely, we calculate how likely it is to occur by chance. In science, we use a threshold, 5 sigma. That's a statistical measure meaning the odds of a result occurring by chance are less than 1 in 3.5 million. When you reach 5 sigma, you can claim a discovery. You can say, this is real. The Higgs boson was confirmed at 5 sigma. Gravitational waves were confirmed at 5 sigma. 5 sigma is the gold standard. 3I Atlas didn't reach 5 sigma. But it came close. On November 27, 2024, a paper was published in Nature Astronomy that attempted to quantify the cumulative improbability of 3I's observed characteristics. The paper was titled Statistical Analysis of Anomalous Properties in Interstellar Object 3 Atlas. The lead author was Dr. Gregory Laughlin, an astrophysicist at Yale University specializing in planetary dynamics and statistical inference. Laughlin's team didn't claim to have answers, they claimed to have done the math. The paper calculated the probability of each observed anomaly occurring naturally, based on known physics, chemistry, and observational precedents. Then it calculated the joint probability, the likelihood of all the anomalies occurring together in the same object, assuming they were independent events. The probabilities for each anomaly: hyperbolic trajectory passing within 0.3 AU of Jupiter, 1 in 20,000. Based on Monte Carlo simulations of random interstellar trajectories, hydrogen line radio emission with 11.7-hour periodicity, 1 in 5,000. Based on the detection rate of similar signals in radio surveys, excluding instrumental false positives, color change from blue-white to amber-red without thermal cause, 1 in 10,000. Based on known material properties and spectroscopic precedents, dust tail bent 11 degrees off antisolar direction with no detectable gas, 1 in 2,000. Based on observations of comets and modelling of tail dynamics, transient albedo spike lasting 4.2 hours, 1 in 3,000. Based on the rarity of similar events in asteroid and comet-like curves, spectroscopic composition showing pairs, silicon carbide, silicates, and metallic oxides, 1 in 8,000. Based on the rarity of such combinations in meteorites and small solar system bodies, each probability was estimated conservatively. The paper included sensitivity analysis showing how the probabilities changed with different assumptions. Even with generous error margins, the numbers held. The joint probability, assuming independence, was calculated by multiplying the individual probabilities 1 raised to 20,000, x to 1.5,000, x 1 to 10,000, x 1 to 2,000, x 1 to 3,000, x 1 to 1,000. 1 in 4.0 are 10 to 19. That's roughly 1 in 48 quintillion. To put that in perspective, the odds of winning the Powerball lottery are 1 in 292 million. The odds of being struck by lightning in your lifetime are 1 in 15,000. The odds of all of 3I's anomalies occurring by chance are 164 million times less likely than winning the Powerball. But there was a critical assumption: independence. The anomalies might not be independent. If they're connected, if one anomaly causes or correlates with another, then you can't simply multiply the probabilities. You need a more complex model. Laughlin's team tested for correlations. They checked whether the colour change correlated with the radio emission. It did. Both had the 11 on 7 hour period. They checked whether the trajectory correlated with the composition. No clear link. They checked whether the albedo spike correlated with the tail. No temporal overlap. Some anomalies were correlated. Most were not. Even accounting for correlations, the joint probability didn't change dramatically. The revised estimate, using a Bayesian network to model dependencies, was roughly 1 in 8 trillion, still astronomically low. The paper's conclusion was carefully worded. The cumulative probability of 3I Atlas's observed properties occurring naturally is extremely low. While low probability does not imply impossibility, it does warrant consideration of alternative explanations. We do not propose a specific alternative, but we suggest that the scientific community should apply the same standards of rigor to all hypotheses, natural and otherwise, and evaluate them based on evidence, not prior assumptions. That last sentence was a diplomatic way of saying, maybe it's time to talk about the thing we've been avoiding. The paper passed peer review. It was published on November 27th. The response was immediate. Dr. Avi Loeb published a blog post the same day. The title, "When the Odds Are 1 in 8 Trillion, Occam's Razor Cuts Both Ways." In the post, Loeb wrote, Occam's razor, the principle that the simplest explanation is usually correct, is often invoked to dismiss extraordinary hypotheses, but Occam's razor also applies to probability. When the odds of a natural explanation are 1 in 8 trillion, that explanation is no longer simple. It requires an extraordinary coincidence. At some point, invoking coincidence becomes less parsimonious than invoking design. I'm not claiming 3I is artificial. I'm claiming the data demands we test that hypothesis rigorously, rather than dismissing it based on philosophical preference. The post was shared 22,000 times. It was quoted in news articles. It was debated in academic forums, on social media, in coffee shops and dinner tables. The SETI Institute issued a statement on November 28th. The statement was measured but open. The statistical analysis published in Nature Astronomy is rigorous and highlights the unusual nature of 3I Atlas. While we do not endorse any specific interpretation of the data, we agree that all hypotheses should be evaluated based on evidence. The possibility of a technological origin, while unlikely, cannot be dismissed without investigation. We are coordinating with international partners to prioritize observations of 3I during its remaining time within observational range. NASA issued a statement on November 29th. It was more cautious. NASA is committed to the scientific investigation of interstellar objects and all phenomena that expand our understanding of the universe. The data regarding 3I Atlas is intriguing and warrants continued study. We caution against premature conclusions and emphasize the importance of peer-reviewed analysis and reproducible observations. The Vatican Observatory, yes, the Vatican has an observatory, staffed by Jesuit priests, who are also trained astronomers. issued a statement on November 30th. It was surprisingly direct. The question of whether we are alone in the universe is both scientific and theological. The discovery of extraterrestrial life or extraterrestrial technology would not challenge the teachings of the Church. It would expand our understanding of God's creation. We support the rigorous investigation of 3i Atlas and trust that the truth, whatever it may be, will be revealed through diligent inquiry. The debate was no longer confined to academia. It had gone mainstream. It was on the news. It was in political discussions. It was in sermons. And the clock was ticking. 3i was now magnitude 23. By mid-December, it would be too faint for spectroscopy. By February, it would cross the heliopause. After that, it would be gone. The odds were 1 in 8 trillion. The window was closing, and the question was no longer what is 3i, it was what do we do now. Sometimes the universe whispers, and sometimes it hands you a statistical anomaly so extreme that ignoring it becomes harder than accepting it. Chapter 14, December 8th, The Last Light, December 8th, 2024. 3i Atlas is magnitude 24. For context, magnitude 24 is about 16 million times fainter than the faintest star you can see with your naked eye on a clear, dark night. It's at the edge of what the Hubble Space Telescope can detect. It's beyond the reach of most ground-based telescopes, even with long exposures. 3i is now 2.3 astronomical units from the Sun, about 344 million kilometres. It's moving at 33 kilometres per second, outbound toward the constellation Pisces. In 2 months it will cross the heliopause. In 5 months it will be too faint for even the largest telescopes to track. The observation window is closing, not gradually, rapidly. Every day the signal drops. Every day the data gets noisier. Every day we lose a little more of the chance to understand. On December 8th, NASA announced a proposal. The proposal was for a deep space probe mission to intercept 3i Atlas before it crosses the heliopause. The mission was called Project Tether, a name chosen to evoke the idea of holding onto something before it slips away. The mission concept was ambitious but technically feasible. A lightweight probe, no more than 500 kilograms, launched aboard a SpaceX Falcon Heavy rocket. The probe would carry a nuclear thermal propulsion stage for the Trans-Jupiter cruise, using Jupiter's gravity for a slingshot assist. After the assist, the nuclear stage would ignite, adding 15 kilometers per second to the probe's velocity. Total velocity relative to the Sun, approximately 50 kilometers. Flight time to intercept, 14 months. The probe would carry 4 instruments: a high-resolution camera, capable of imaging 3i at sub-meter resolution during the flyby, a spectrometer for measuring composition across visible, infrared, and ultraviolet wavelengths, a magnetometer for detecting magnetic fields, a dust analyzer for sampling particles in 3i's tail or near-surface environment. The flyby would occur at a relative velocity of about 20 kilometers, too fast to slow down and orbit, but slow enough to capture detailed data during a few minutes of close approach. The estimated cost, $1.1 billion. The timeline, launch by May 2025, 5 months away. The announcement was made at a press conference at NASA headquarters in Washington, D.C. The speaker was Dr. Nicola Fox, the Associate Administrator for NASA's Science Mission Directorate. Her statement was direct. 3 Atlas is the most scientifically significant object we've observed in a generation. Its properties challenge our understanding of interstellar objects, planetary formation, and the processes that occur in the space between stars. We have a narrow window to study it up close. After that window closes, it will be gone forever. The scientific return from a flyby mission would be transformative. We believe this mission is worth pursuing. The proposal was not a commitment. It was a request for funding. The actual appropriation would need to go through Congress, through the budget reconciliation process, through committee hearings and debates. The timeline was tight, too tight for a normal mission approval process. Dr. Fox acknowledged this in the Q&A session following the announcement. A reporter from Space News asked, "Is 5 months really enough time to design, build, and launch a mission like this?" Fox's response, "In a normal timeline, no. But this isn't a normal situation. We have existing hardware, propulsion systems, instruments, spacecraft buses that can be adapted. We have launch vehicles ready. We have the expertise. What we don't have is the funding approval and the political will. If Congress acts quickly, we can make this happen. If they don't, the opportunity is lost. The proposal was met with mixed reactions. Some praised it as visionary. Dr. Alan Stern, the principal investigator for NASA's New Horizons mission to Pluto, said in a tweet, "This is exactly the kind of bold, time-sensitive science NASA should be doing. We chased Pluto. We should chase 3I." Others criticised it as rushed and reckless. Dr. Heidi Hamel, a planetary astronomer and vice president of the Association of Universities for Research in Astronomy, said in an interview with Nature, "I support the scientific goals, but I'm concerned about the timeline. Missions this complex take years to plan. Cutting corners to meet a deadline increases the risk of failure, and a failed mission doesn't just waste money, it damages credibility and sets back future efforts." The debate was practical, not ideological. Everyone agreed that studying 3I was important. The question was whether a rushed mission was better than no mission. On December 10th, a bipartisan group of senators introduced a bill to fund Project Tether. The bill allocated $1.2 billion, slightly above NASA's estimate, and included language, fast-tracking the mission approval process, bypassing some of the standard review requirements. The bill was controversial. Some lawmakers argued it was fiscally irresponsible during a budget deficit. Others argued it was a waste of money on a speculative mission. Still others argued it was essential, a once-in-a-generation opportunity that justified extraordinary measures. The bill was debated in committee on December the 12th. No vote was taken. The committee chair stated that further review was needed. Meanwhile, 3I continued its journey, fading, receding, indifferent to the politics. By December 15th, 3I was magnitude 24.5. Ground-based spectroscopy was no longer viable. The last high-quality spectrum had been captured by the Keck Observatory on December 8th. After that, the signal was too weak. The amateur astronomy community continued to track 3I's position. The Interstellar network logged photometry whenever possible, though the object was now at the edge of detection for their telescopes. The data was patchy but consistent. The 11.7-hour period was holding. The brightness continued to fade predictably. The radio signal was still detectable. The Very Large Array conducted observations on December 14th and December 17th. The 1.42 GHz signal was present, still pulsing with the 11.7-hour period. Weaker now, but still there. On December 18th, Dr. Frank Marquis organised a public webinar titled 3 Atlas: What We Know, What We Don't, and What Happens Next. The webinar was hosted by the SETI Institute and broadcast on YouTube. Over 300,000 people watched live. The webinar included presentations from several scientists. Dr. Helena Vasquez, who had first observed the colour change, summarised the spectroscopic data. Dr. Davide Farnocchia discussed the trajectory and the Jupiter flyby. Dr. Yuki Tanaka reviewed the composition and the inconsistencies. Dr. Gregory Laughlin presented the statistical analysis. And Dr. Avi Loeb discussed the implications, both scientific and philosophical, of the data. Loeb's presentation was the most widely shared. He concluded with this statement: "We are at a crossroads. We have data that doesn't fit our models. We have a statistical anomaly so extreme it demands explanation. We have a closing window to investigate further. And we have a choice. We can proceed cautiously, conservatively, waiting for certainty that may never come. Or we can proceed boldly, accepting uncertainty, willing to test uncomfortable hypotheses. History will judge us not by whether we were right, but by whether we tried." The webinar ended with a Q&A session. One question, submitted by a viewer, stood out. "If we don't catch 3I, and it turns out to be something extraordinary, will we regret letting it go?" Marcus answered, "Yes, absolutely. We will regret it. But regret is a luxury we only get if we survive to feel it. Right now, our job is to do the best science we can with the time and resources we have. Regret comes later." By December 20th, the funding bill for Project Tether had stalled in committee. No vote was scheduled, no timeline was set. On December 22nd, NASA issued a statement acknowledging that without immediate funding approval, Project Tether could not meet the launch window. The statement concluded, "We remain committed to the study of interstellar objects and will continue to explore alternative mission concepts for future opportunities." Translation: the mission was dead. The reaction was grief. Not dramatic grief. Quiet grief. The kind that settles in when you realise something important is slipping away and there's nothing you can do. On December 24th, Christmas Eve, Dr. Emily Reyes, the radio astronomer who had first detected the 1.42 GHz signal, posted a thread on X. The thread read, 3i Atlas will cross the heliopause on February 11th, 2025. After that, it's in true interstellar space, beyond our reach, beyond our instruments. Gone. We had 4 months to study it. We logged hundreds of observations. We gathered more data than we did for Oumuamua or Tui Borisov. We did good science. But we didn't answer the big question. We don't know what it is. We don't know where it came from. We don't know if it's natural or something else. And now, we won't. Because the window is closing, and we're letting it. Maybe that's okay. Maybe the universe doesn't owe us answers. Maybe the whisper is enough. But I can't shake the feeling that we're going to look back on this moment, this object, this data, this choice, and wonder what we missed. Merry Christmas. Hug the people you love. Look up at the stars. Somewhere out there, 3i is still flying, still changing colour, still transmitting, still being whatever it is, and we're still here, watching it go. The thread was retweeted 47,000 times. On January 15th, 2025, 3i Atlas passed magnitude 25. The last reliable photometry was captured by Hubble on January 12th. The last radio detection was by the VLA on January 18th. After that, the signal dropped below the noise floor. By February 1st, 3i was too faint to track. Its trajectory was extrapolated based on earlier observations. The predicted crossing of the heliopause was February 11th, 2025, at approximately 14 were UTC. There was no ceremony, no official announcement, just a date on a calendar and a moment when an object passed from hours to not hours. On February 11th, Dr. Frank Marshis posted a single image on X, a simulated view of the heliopause, with a tiny dot labelled 3i crossing the boundary. The caption read, "Goodbye, traveller. Thank you for the questions." The questions that stay. This is not science fiction. This is February 2025. 3 Atlas is gone. The data remains. The colour change that defied material science. The trajectory that threaded through Jupiter's gravity well with odds of 1 in 20,000. The radio signal at 1.42 GHz, pulsing every 11.7 hours. The backwards bending tail with no detectable gas. The albedo spike that lasted 4 hours and never repeated. The composition that combined materials from incompatible environments. Each anomaly by itself has possible natural explanations, unlikely explanations, speculative explanations, explanations that require invoking processes we've never observed, materials we've never seen, coincidences we've never documented. Together, the anomalies form a pattern with a cumulative probability of roughly 1 in 8 trillion. We didn't catch 3i, we didn't send a probe, we didn't get close-up images or definitive answers. We watched, we measured, we debated, and we let it go. Maybe that's the right choice. Maybe caution is wisdom. Maybe we avoided the mistake of over-interpreting ambiguous data, of chasing speculation at the expense of rigour. Or maybe we made the opposite mistake. Maybe we let the most important discovery in human history slip through our fingers because we were too afraid to ask the uncomfortable question. We'll never know, because 3i is gone, and the next interstellar visitor might not arrive for 5 years, 10 years, a generation. But the questions aren't gone, they're staying with us. What is the threshold for extraordinary evidence? How do we balance skepticism and openness? How do we know when caution becomes paralysis? And the biggest question of all, are we alone? 3i didn't answer that question, but it asked it, loudly, in wavelengths and trajectories and chemistry, and we listened. For a few months, across a few continents, with a few dozen telescopes and a few hundred scientists, and a few 100,000 people watching online, we listened. We didn't get the answer, but we heard the whisper. Sometimes the universe speaks in numbers, in probabilities, in patterns that don't fit. Sometimes it changes colour just to see if we're paying attention, and sometimes the most important thing we can do is admit that we don't know, that the data is strange, that the models don't work, that the universe is bigger and stranger and more surprising than we ever imagined. 3i Atlas is leaving, but the questions it asked are staying with us, and maybe that's the point. Before you go, Tell me in the comments. Do you think 3i was natural? Do you think we should have sent a probe? Do you think we'll regret letting it go? And if you've made it this far, if you've spent 22,000 words with me, following an object through the dark, tracking its anomalies, feeling the weight of its implications, then you're part of this story now. Thank you for listening. Sometimes the universe whispers. This time, we listened. And maybe, someday, it will whisper again. This is not science fiction. This is right now. End titles. Card 3i's Atlas crossed the heliopause on February 11th, 2025 at 1417 UTC. It is now 127 astronomical units from the Sun, travelling at 33 kilometres per second. Outbound, not coming back. The data is archived. The debate continues. The universe is still whispering. Are we still listening?